Hey guys, what's going on? So what you're watching here is a clipped video from a whole video that you'll be able to access if you become a member on Patreon or if you become a member on my YouTube channel. These videos are relatively difficult to make because I'm using multiple sources to compile all the information together. And so with your contribution, I'll be able to make more content as well as create exclusive content for those of you who are really invested into this channel, who really want to understand a lot of advanced physics and life sciences. So with that being said, make sure to hit the like and subscribe button. Make sure to go onto the Patreon page and you can contribute there. You can also become a member here on YouTube. So let's now get into the topic. Hey guys, what's going on? So today we are going to be talking about the physical relevance of probability distributions. So we sort of introduced the idea of these distributions in the last video. We talked about the binomial distribution, we talked about the negative binomial distribution, we talked about the Poisson distribution, and we talked about the geometric distribution, but we sort of only really introduced those. In this next video, we're going to go into how they're more physically relevant, what kind of questions they answer, and then from there we're going to get into moment distributions or moment generator functions, which are quite interesting, and they're going to raise their ugly head in quantum field theory, which is going to be fun to talk about. But before we go into that, make sure to hit that like and subscribe button. Make sure to go into my Patreon channel or my Patreon page if you want to support the channel, and you can become a member here if you want to support that way as well. Also, as I've mentioned before, the aim of these is to really build a business. Okay, I'm really interested in trying to get advanced topics in math, physics, science to the general public, and in order to do that, I need some money. In order to get some money, I'm putting out these videos, but I also have a very vested interest in just informing the public on advanced science in general. So, with that being said, that's what your contributions are going to be going to. Let's get into it now. So we're talking about the physical relevance of probability distributions today. This is going to be sort of the stepping stone into talking about moment generator functions, because moment generator functions are really going to be the end all for when we're talking about this kind of stuff, and they're really going to help in helping us understand statistical fields within the context of quantum field theory as well. And so we're going to go over that stuff as well. This is going to take a few videos. So what is a probability distribution function? I personally like to think of it as a distribution over experiments. So we're going to stick with the coin example here, but we can do this for other examples. But suppose you drop one coin. Okay, when you drop one coin, it'll land heads or tails. In this case, it's landed heads. And we can ask the probability. We can ask the question, what is the probability of getting heads? Okay, so we sort of asked this before. The probability is 50% if it's a fair coin. And so every time we drop the coin, that we're going to call that an experiment in this case. The probability of the coin being heads, we're going to call P. And in this case, if we're just dropping one coin and calling that one experiment, it's going to be 5%. Tails is going to be 1 minus P, right? So in the case of this is 0.5, this is going to be 0.5 also. And this is what's called a Bernoulli probability distribution. This is the most simple distribution, if you will, in which the probability of x equals 0 is 1 minus p, okay, because x equals 0 is associated with the head state, and x equals 1 is going to be p, which is the tail, this is the tail state, this is the head state. So now suppose, let me move this up a little bit, make sure my voice is, there we go. Now suppose we drop a coin twice. So there are 4 possible outcomes now. So flip a coin once, record that, flip a coin again, record that, okay? 2 times, you call that an experiment, okay? So you're flipping it twice, you call that an experiment. There are 4 possible outcomes in this case. You flip the coin once, you get heads, you flip it again, you get heads again. Okay, bag that experiment. Next experiment, we could get the possibility of first coin is heads, second coin is tails. We can then toss. We can also get an experiment that looks like this, and an experiment with an outcome that looks like this. Okay, but in this case, two of the states are degenerate, right? These two, right? And so we really only have three possible outcomes if we're not marking the coins, right? So we're not going to mark the coins, and so these are the states that we get, right? So one head or two heads, one heads, one tails, and two tails. Okay, so up to this point, we've been asking about the probability of a coin, or the probability of each occurring. As we discussed in the last video, we saw that the answer to this is given by the binomial probability distribution function, or distribution. Let's take a look at what happens if we're just interested in n equals 1, right? So I put these n equals 2, n equals 1, n equals 0. Remember, n refers to the number of heads, right? We're really just interested in the number of heads, okay? And so this is our equation here, right? So our binomial probability distribution is given to us by this equation, right? So where if n equals 1, this is n. This is big N, right? Big N we can think of as being the number of tosses we're doing, okay? And we have this then, right? So if we plug in, so this is our combinatorial thing, whatever you call it, combinatorial function.